In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note.
All right, hello and welcome everyone to Ether Cosmology episode 71. Tonight I'm going to be doing a recap on the history of classical physics and the meaning of absolute space and the deviation from that presented by relativity after a certain measurement done in 1887. So there's been some confusion lately going on regarding what constitutes as a reference frame or not, and we're going to go into the specific definitions for everything. You look at the origins of how everything has been derived so we can understand the philosophy of what's being put forward so we can understand the physical meaning of mathematics. Cass, I muted your mic for a second there. You were echoing me a little bit. Should be good now. All right. So to start us off here, to get us a little introduction into the door, we're going to distinguish between a reference frame and a coordinate system. And the easiest way to do that is by referencing Wikipedia here to get us a little introduction. So specifically, it talks about how coordinate systems are just a point with origins for an X, Y, Z, T axis. So standard Cartesian coordinates describing spatial points, essentially. And then when you get into a reference frame, specifically, they have it defined as an observational reference frame, and this is in line with in the Einsteinian relativity. The definition of a observational reference frame is given here, where it says that it is to specify the relationship between the moving observer and the phenomenon under observation. So very specific verbiage there, and that is because in Einsteinian relativity, you cannot use an arbitrary fixed point of reference. The the calculations must be done with respect to where the measurement was made and the phenomenon in question. So in the case of like light, for example, it would be the source emitter and the observer making the measurement. So a reference frame contains an observer with a clock and measuring rod to make these measurements. So when we're in this whole presentation is color coded in such a way, which I'll go over it now. So when you see certain colors, you'll know to think of, you'll know to interpret the meaning in a certain way. So blue will be reference frame. Anytime we're talking about where a measurement is being made, where an instrument is, that is in the coordinate system that describes that, that's going to be a reference frame. The coordinate system is going to be the abstraction that describes the 3D spatial dimensions of that reference frame. And that is going to be our X, Y, and Z and T axis.
Wow, dude, nice.
And we can use different Cartesian coordinate systems to describe different geometric shapes, which we'll go over here in a second. And we live in what's called coordinate system simultaneity, coined by my boy Shane. All right. So in relativity theory, reference frames determine that relationship between the moving observer and the phenomenon through Lorentz transformations. So that's going to be very important when we get to that section about how they verify the validity of their claims with mathematics. Time and distance are defined as relative functions of velocity squared over the speed of light squared between the moving observer and the source emitter. And this will be for relativity moving forward. So that's not how it's defined in the classical system, but this is just specific for helping to identify the difference between the two systems, because in one you can make arbitrary frames and use absolute space, and in the other system you can't. So that's the big distinction there, of significance to understand. So here we're going to look at some different spatial parameters that define different geometric shapes: cylindrical, spherical, rectangular, elliptical, etc. And again, coordinate system simultaneity turns out to be true because the only thing that distinguishes these coordinate systems, or the only thing that you need to do to like transform back in between them, is have a common axis and alignment and the corresponding angle transformation to get back to it. So here we're starting off with our rectangular coordinate system defined by the standard XYZ. Then we're going to look at a cylinder coordinate system, which we can have planes that intersect that. So to get back to that coordinate system, to the XYZ, this is the relationship to describe that. So all of these are all equal and valid, and they're all at the same time. So we're just going to breeze through these. They're not of like super significance. It's just to show you guys some cool shapes and the equivalence between them all, because they all look very complex and unique. Maybe some of them would be, mutually exclusive to one another or something. Not the case. There's just a coordinate system correction between them all to get back. So conical, parabola, oblate, spheroid, all of those, all equally equivalent. Just need the corresponding correction and you're good to go. So again, they go more into that on that field theory handbook there, which goes over coordinate systems and differential equations and, how to solve them. All right, so now we're going to get into the definition of reference frames in the Newtonian aspect. And we're going to look at that through the Newtonian philosophy. And our boy Donald Greenwood from the Principles of Dynamics is going to be our guide through the Newtonian reference. He did an excellent prelude into dynamics and the story and the philosophy of reference frames and absolute space and all that. So we're going to summarize a lot of what was contextualized there. So to recap, those coordinate systems, all of these, right, are all mathematically, if you were to assign X, Y, Z axes to them for a coordinate system, for a reference frame, that would be fixed, stationary, non-rotating. And when you get into the definition of a reference frame, you might say, well, what about the Earth? We could use the Earth, right? Well, that might be your first thought because the laws of physics were derived on Earth. But Newton, for philosophical reasons, uh, chose not to use the Earth as that reference frame. Now, when you get into, they say satellites and rocket launches and like long distance ballistic missiles, et cetera, that kind of thing, you would have to use a coordinate system at the center of the Earth to make the correct predictions, because the Earth is, in motion, it's in rotation and all this stuff. So there's going to be deviations at different parts of the scales that you're trying to extrapolate from, they say. So when it gets to predictions for satellite orbits and sending things out into the solar system, they say that they would have to use the barycenter of the solar system, which is the gravitational midpoint where the gravitational potential from the sun and all the other planets have equalized just off center of the center of mass of the sun. So this hypothetical location would be kind of inside the sun, just off center from the center of mass. And this is what they would say is like the stationary spot that everything would be in reference to. So the conclusion is that absolute space exists, just not sure where, even though the laws of physics were derived right here on Earth. So it would make sense that the absolute frame would be Earth, right? So we're going to look at how and why from basic mechanics. That goes over a nice analogy on defining the difference between a reference frame and a coordinate system. And specifically, they make the note that the distinguishing factor between them is that an observer in regards to a reference frame is not to be confused with a human, because humans make mistakes, errors, etc. But what they're talking about when they say observer in a reference frame, they're talking about the place where the instrumentation exists that's making the measurement, which is, free from human error and all that. So they go on this cool little back and forth dialogue between a student and a professor asking about reference frames and the misconception between the two. And that's ultimately the big takeaway, is that reference frame implies observer, observer implies instrumentation making measurement, not a human. And then so you would get into, is the observer stationary or in motion? And if so, with respect to what? And that would be, in all cases, it would be with absolute space. But the way that they want you to look at it, as for how they're going to define an inertial frame specifically, is going to be one that's in uniform relative motion. And we'll get into how they do that and why they feel very comfortable in that position. All right, so we've got our definition of a reference frame, right? We know where this is where the measurement takes place, but what about conceptual reference points? So this goes back to absolute space. So this is this idea that there's this primary inertial frame that is non-rotating relative to the fixed stars. And um, so this is where Newton gets into saying that for uniform transitory motion, there's no absolute reference frame. But for rotation, there is. And we'll look at Newton's bucket here in a second, how he came to this conclusion. But what they're asserting here is that because they can derive an inertial frame from calculus that predicts that there's no inertial forces when you're in uniform transitory motion, that they use that as their jumping off point for there being no reference frame for the motion to be relative to other than, somebody else, unless it's for a rotation. So they have this special case where they have to have this area that is fixed, non-rotating, but they just don't know where to put it. So Newton was conceptualizing that it would be in the center of the solar system, at that very center that we talked about earlier. And then a guy named Mach will suggest that it's with respect to the distribution of the mass of the entire universe and the Earth. But we'll cover that as we go forward. But this is just to reiterate, we need this fixed space for this motion to be relative to, because rotation turns out to be absolute through the Newton's bucket analysis, which we'll cover here shortly. So in tandem with absolute time space, there's absolute time. And this is going to be relevant for how they derive a reference frame with calculus to determine the validity of the inertial reference frame and how it doesn't predict any inertial forces on it. So time is absolute for all observers, and it's independent of physical objects in motion. So Mach's perspective of it was that time is an abstraction based on physical changes like the relative motion, and that relative motion is going to be relative to that mass distribution of the universe. And then, the time is just going to be an abstraction based on relative motion within that system. So yeah, he was just kind of putting forward that using relative motion, we can take comparisons with different clocks to make measurements and narrow down absolute time that way, kind of. But he didn't conceptualize it as like an absolute thing. So absolute time. So the benefits of this, of assuming absolute time for all observers, is you can derive through velocity composition a change in respect to the acceleration over time, which would give you, which would tell you if that frame is experiencing an inertial force or not. So absolute time and space are the backbone of defining an inertial frame, as in uniform relative motion, and that would be relative to what? And some would say the Earth. That would be all relative to the Earth, as we're going to show when we get into dynamic predictions, because the way that this is going to be presented philosophically by the relativist and modern mainstream is that because of this, there's no absolute space, and we could use whatever reference frame we want, et cetera, et cetera. But it has no actual meaning to it. But we're going to show the measurements that show that it has meaning, because there's measurements that are made with respect to absolute time and space. Get into that too as we go on. So here's more about how they derive a reference frame using the velocity summation here. So they've got a two-particle system, VA and VB. They're going to be moving at a constant velocity, and when we add them together, we have their relative velocity. And when you take a derivative of that, there's no change in time after you take, well, you'd have to take two measurements, right, to get the change. But if there's no change in this relative velocity, then you predict that there's no inertial forces, and from that you're good to go. So that's kind of their jumping off point. But this is a really one-sided analysis because in this particular case, F equals ma would apply in these frames. Similarly to how if you were in a train moving at a uniform velocity, you wouldn't experience any inertial forces. If you were juggling balls, for example, it wouldn't, you wouldn't move out from underneath them. If you put the balls down on the floor, they wouldn't roll to the back of the train. So in this instance, it does make that prediction, but we can go over different analysis of dynamics and mechanics to show that only with respect to the lab frame do these, can you make the correct prediction every time? So this one-sided analysis is kind of how they uh, start the trick to get you to believe in this arbitrary nature of things. So the assertion is that dynamics is valid by a convenient choice of coordinate system with respect to some other preferred frame, possibly the fixed stars or the barycenter. So the dynamics is only valid when you're using the lab frame. All reference frames being valid for relative motion is only valid in kinematics. All right, so from assuming absolute time and space, we can have absolute units for length, for distances, time, and force. And if we equate force and mass together, we can use this to derive all the units of measurement for mechanics. So length, time, force, mass, velocity, acceleration, work, angular velocity, so on and so forth. All of these units derive from these basic assumptions, and these are what make the correct predictions. These are what validate experimental hypothesis. When your equations, make the correct predictions, that's when you get validated, right? So all of this stems from like this fundamental basic concept. And then, so like, for example, we have mass, right? Well, mass is additive. So we can do, say you have 5 pounds of mass, something that weighs 5 pounds, and you have something that weighs 15 pounds, you now have 20 pounds, right? And that'll be super important later when we get into the Einstein tensor stuff. But this is all derived from this concept of absoluteness, right? Okay, so see, when they get into the math, they talk about how, both sides of the equation have to be symmetrical. You can't have units that are not the same dimensions. So there's they have a specific set of rules for validating their mathematical framework that they have to follow. And if you're not following the rules of the structure, then what you're doing, isn't valid. So within this framework, there's rules and structures for how it's applied and how you can interpret reality from this. So a quick note on the definition of mass, I thought was an interesting note in this, in the Principles of Dynamics book. He talks about the circular definition of mass, where Newton defined mass as a quantity of matter, which is calculated by the product of the volume and density. And that's very circular because to find density, you need mass over volume, and to find mass, you need density times volume, and to find volume, you need mass over density. So it's just a circular definition of replacing different variables to give that definition to it, rather than kind of giving you like an operational definition. And then, of course, when you get into the relativistic system, mass can change. So as a function of energy and velocity. So
That's crazy. I didn't realize that whole definition was just a setup for E equals MC squared. Wow.
Right? Yeah. Okay. All right, cool. So now we're going to get into a dynamic analysis and go over some scenarios to see if we can find which reference frame makes the correct prediction. So the Newtonian reference frame is one that accurately measures acceleration based on Newton's laws of motion. It is a rigid coordinate system where a particle in motion follows Newton's laws. And what that would mean is, suppose you're a little lad on a little particle moving at a constant velocity. same thing as the train scenario. You're moving at a constant speed. You're not going to feel any inertial forces. That's all that means, is that it's moving with respect to some absolute fixed point. A reference frame fixed on Earth works well for short distances, traveled, and small velocities, as they tell us. Because of Earth rotation, they have to make these corrections, etc. Whether or not those are manifest, we're ignoring that for now and just taking this as is. So the ECI frame is centered at the center of the Earth with its axis non-rotating relative to the fixed stars. So this is where some people would say, the gyroscope isn't moving with respect to the center of the Earth, or some people might say it's not moving with respect to the fixed stars, that kind of thing. So this is the abstraction that they're trying to put they're trying to put this frame in, and obviously in the center of the Earth is it's a part of the Earth system, but it's not the Earth. So they're just kind of further trying to abstract it. It can't be the Earth, but it can be hypothetically the center of the Earth, right? But not the Earth itself. It's kind of what they're going with there. So that's the philosophical implication there for Newton and Mach. And then of course Mach said that it was with respect to the distribution of mass of the universe, which we will cover as we continue. So we're going to do some analysis here based off of this. So using a little null hypothesis, we could say that there is no universally preferred frame for motion and for making the dynamic predictions of future motion in all scenarios. So you can just use any frame arbitrarily. And then our hypothesis would be that the laboratory frame serves as the preferred reference frame for making dynamic predictions of future motion in all scenarios. And the dynamic analysis for conservation laws, energy potential, etc., the lab frame will make the correct prediction every time. And then a few slides back, they talked about Newtonian mechanics requires an absolute frame for rotation, but we'll see that this also applies for translational motion, not just acceleration, but also uniform translational motion as well. Yeah, we'll get into it now. So starting with Newton's bucket, where we have Newton spinning a bucket, and he's going to apply his centripetal equation to see if he can predict what's going to happen to the water inside, how it's going to curve, if it's going to form a hyperbola or not. And he applies his equation for the velocity of the bucket, and he makes the correct prediction that it's going to curve. Now, suppose you could put a lad inside the bucket, and he would be standing there. He would predict that his velocity is 0 and everything is spinning around him. So when he applies Newton's equation, he gets the wrong result for the force because he predicts that he has no velocity. Yet there's a curve in the water. So Newton came to the conclusion that to describe this, there had to be an absolute space for this to be relative to, but he wasn't sure where to put it, whether or not if it was the Earth or if it was in space. And so for philosophical reasons, being a Copernican lad, he put it in the sky instead of the Earth. All right. So yeah, when you do this analysis where the bucket is moving with respect to the lab frame, you make the correct prediction. When the bucket is spinning, or when you make it with respect to yourself in the bucket, you make the wrong prediction. All right, so to continue that, we have Bennett's hiker, an example given where a driver in a car is accelerating towards a hitchhiker. In the driver frame, he predicts he would feel an acceleration because he's moving. If he tried to apply that to the hitchhiker, he would make the incorrect prediction. The hitchhiker, seeing the car moving towards him, would predict that the driver is going to feel a force on him, which makes the correct prediction, and that the force that he's going to feel because he is stationary is that he's not going to feel one. So he makes the correct prediction being stationary. So if you're not moving with respect to the lab frame, you make the correct prediction that no forces will be on you. And this is the linear version of the rotation. So instead of a bucket and rotation, we have linear acceleration now, where only with respect to the lab frame, the correct prediction is made. So to continue off of that, we can do Foucault's pendulum and take the frame of the plug bob versus the lab frame, and we could invert the two to see which to do the work for the swinging of the plumb bob, because they say that the plumb bob swings because the Earth is rotating. So when we do an analysis for the kinetic energy prediction, if these two reference frames are equivalent, the uniformly swinging back and forth plumb bob and the Earth, we get a prediction that would basically send the plumb bob into outer space. The reference frames are not equivalent. There's an insane amount of energy potential that's unmeasured in reality. So when you go through all of that, none of it is actually meaningful in the way that they've started their analysis for how they jumped off to get into this point where they started with, well, F equals ma in a scenario like a train, right? Well, let's take a look at the train moving at a constant uniform velocity and see how that turns out. So we have an observer in the train and he's juggling balls. So the balls have a vertical component and they have a horizontal component. But in the frame of the train, you're not aware of your horizontal component. So when you do your analysis, you make the wrong prediction for the amount of energy that the balls have. When you do the analysis with respect to the lab frame, you have the horizontal component for the velocity of the train and the component for the velocity of the balls going vertical. And you can now have the correct energy output for the system. So even in this mythology of being in a isolated system that's in uniform transitory motion, you still can't make the correct prediction unless it's with respect to the lab frame. So when you get into the definitions of the choice of reference frame being arbitrary, and it's just for choice of convenience, it's not at all. The lab frame is absolute, and it makes the prediction every time. So the definition given by Einstein and the boys for uniform transitory motion and arbitrariness for philosophical reasons is invalid. We can show it mathematically very easily. And so the inertial frame would have to be redefined as being fixed, stationary, non-rotating, and absolute, because that is the only thing that actually makes the correct prediction here. You can do the same thing with Bennett's biker, where you have a biker on a ramp and you could do the analysis with the mass of the biker going down with the force of gravity. And you can predict how much energy he'll have when he comes down this ramp versus if the mass of the earth is rising up to meet the biker to facilitate that motion. And again, that energy output would send you boy out into space. And that's not what's measured. So by the way, real quick, since we have a diverse group here, like how would we get flat earthers to acknowledge the validity of a lab frame analysis using something like the mass of the earth? Don't worry, boys. It's just a constant that we're using. It doesn't have to have any physical meaning. If you wanted to, you could take each individual experiment that you're doing and just say like, okay, we're going to section out this area of the ground and go, 10 feet deep and say that this weighs, 2,000 pounds or whatever it is. And you would just have that as your reference frame for comparison. But instead of doing that every time and defining things arbitrarily, you can just use a constant to do the whole thing. Either way, the main point is to show that there's going to be a disproportional amount of energy predicted and that it's not a valid way to interpret things if your framework is verified through energy conservation and things like that, right? That would be nonsensical. All right. So let's see. We have Mach's analysis of absolute space. Again, he notes here for Newton's bucket, he says, Newton's experiment with the rotating vessel of water simply informs us that the relative rotation of the water with respect to the sides of the vessel produces no noticeable centrifugal forces, but such forces are produced by its relative rotation with respect to the mass of the Earth and the other celestial bodies. So here, Mach was half right. It is with respect to the Earth, mass of the Earth, right? You could definitely use that. And it is not with respect to the other celestial bodies. Yeah, through that analysis, though, we have shown that there is one primary inertial frame that supersedes all other arbitrarily defined ones, and especially ones that are in motion relative to the primary inertial frame. So as of yet, everything seems really good and positive. what kind of potential problems could we have? We've got this nice system where we can have units of measurement. We've got the lab frame that's just inertial enough, but when it comes down to it, we'll put the inertial frame in the stars so that nobody has to, believe that the Earth is stationary or fixed or anything like that. We'll kind of take that off the table. But we have this nice way to calculate things, make predictions, verify hypotheses. We're having a great time. What's the issue? Oh no, guys, in the 1800s, they realized that they could measure velocity through the fringe patterns in light. The proportion, the fringe difference, the fringe pattern, the square of that is proportional to the velocity that they're trying to measure. So they had all these mathematics. They had specifically when they started applying Newtonian dynamics to the sky with Kepler's law through a little algebraic shuffling, they really committed to the idea that, the Earth was in motion, that the Earth weighed this amount, that the sun weighed this amount, and everything could be you could backwards derive all the masses of the other planets. And because of the mass attracting mass relationship that first established the mass of the Earth based off of the torque angle of lead balls in a shed from a guy in the, what was it, the 1700s, Shane? Based off of all that, they're using these variables and all this to tell us not only like why where the planetary bodies are going to be, but like why they're moving, which is crazy. And they got all the character stats for them too, like how much they're made of or how much they weigh, what they could possibly be made of and all this stuff. So they got super carried away with that, but they had the technology to actually measure their velocity through space using light, using an interferometer. So if you take an interferometer, you split a light beam orthogonal to itself in such a way that it either completes a circuit or it just completes a 90-degree angle to itself there and back and comes back. You can measure the phase difference between the north-south and the east-west sides. And that will give you that the difference in timing produced by that is proportional the square of the velocity in question. So they had the exact amount for how much they would derive for a velocity of 30 kilometers a second to substantiate Newtonian dynamics and Kepler's laws. And when they took the measurement, they measured 4 to 6 kilometers a second. They had an air tolerance of 2 kilometers a second. So they were well outside of their air margin. I'm sorry, they measured 6 to 8. My bad. They measured 6 to 8. So they were well outside of their air margin there. And they didn't really know what to make of that because their philosophy and measurements thus far interferometrically are showing that they could make measurements with respect to absolute time and space to produce these fringe patterns. So they were in quite a predicament here. So we're looking at the measurements from Michelson-Morley and how they answered them. So the displacement should be 2d, which is just the 2 times the distance that light had to travel. So 11 meters times the velocity squared, which would be 30 kilometers a second, over v squared, which would be the speed of light in the corresponding wavelength that they had. And that would come out to 2d times 10 to the minus 8, which is going to be the fringe displacement for them. So they knew exactly how much it was going to be for their corresponding wavelength of light. That would equal, when you square that, it's going to come out to 30 kilometers a second. Now, what they measured, when they square it, comes out to 6 to 8 kilometers a second. So to answer that, oops, you're hot micing a little bit, Joe. I'm going to mute you for a second. So they had, they didn't really know what to do with that. And there was a guy named Lorentz who had a static ether theory who was using a Lorentz transformation to say that time and space, rigid bodies that move through this static ether compress as a function of the square of their velocity over c squared. So with that, he was saying that, okay, the reason that we didn't get the fringe pattern that corresponds to 30 kilometers a second is because we actually shrank by that amount. Instead of having the amount predicted by absolute space, we actually shrank by that amount because all motion is relative, to this static ether, but moving through it will compress bodies by a function of that of their velocity. Now, in order to propose this, the measurement would have had to have been lower than 2 kilometers a second for the to hit their margin of error, but they were outside of their error bar. They were at 6 to 8. So they did what any reasonable what any reasonable person would do in this scenario. They just rounded it down to the nearest zero and said,
Changed the hypothesis retroactively.
yeah, they just failed to detect instead of failing to detect the relative velocity of the Earth around the sun relative to the ether, they failed to detect the ether, guys. That's what they went with. They said that they can't do that. Now, this is obviously not a great position to be in. So they're gonna need to supplement it a little bit. So that's where Einstein comes in, and he's like, "Hey, we have this beautiful framework here of matter compression with a proposed mechanism that we could just change a little bit, but we got to change the philosophical interpretation up a little bit. So let me whip out this 1905 paper and lay out the philosophical foundation for how we're gonna lay everything out." So he starts off by talking about how the laws of electrodynamics are valid for all frames of reference with which the laws of mechanics hold good. The laws of mechanics being the ones we went over doing the dynamic analysis. So Newton's laws of motion, predict future dynamics, all these things are going to be valid in inertial reference frames. So inertial reference frames are going to be defined as being in uniform transitory motion with not respect to absolute space, but just respect to some other person or thing that's in motion is how they're going to do that. And then specifically, the second postulate off of that is going to be because of the results of this measurement where they took it from 6 and said it was 0. Well, it turns out that if you're in if you're in an inertial frame, the speed of light is going to be independent of your state of motion of the emitting body. And although it doesn't say observer here, he is talking about specifically between the emitting body and the observer, because that is the answer to this experiment to begin with. So it would be like there's only one real way to interpret that. And then when you go through the entire paper, the instances of time, how he defines time, it's not with respect to absolute time or something arbitrary. It's reference frame dependent on and specifically on the velocity of the observers. So there's a real quick note here after he makes his statement about where his equations apply and what the speed of light has to do with them in relation to inertial frames. He goes on to say that the introduction of a luminiferous ether will prove superfluous inasmuch as the view to be developed here will not require an absolutely stationary space provided with special properties, nor assign a velocity vector to a point in empty space in which electromagnetic processes took place. So an absolutely stationary space with special properties would be this static ether that material bodies are moving through and they're being compressed by. He's saying we don't need that as a mechanism for light to propagate through. We don't need a material medium because one of the implications of being in a medium is that if you're in a medium, all motion is going to be relative to that. So you can kind of think about how sonar works with submarines using a range measurement equation and the speed of sound in water. So all motion is going to be relative to that to the water in that. And based off of timing differences, that's how you would establish distances in that. So, and they're saying like, well, we tried to do a timing difference situation here, but somehow the timing turned out to be such that we couldn't determine any distance change. So, anyway, following that line of logic there, that's why he's making specific points to say, this is where my theory differs from Lorentz's. This is where we're going to deviate from this conception of absolute, because Lorentz's theory had no problem with absolute for relativity for simultaneity being absolute, but for the deviation with Einstein, simultaneity is going to be relative, meaning two different outcomes are going to have to come out of that. But anyway, and then assigning velocity vector points to empty space. Now, this is going to be important for the mathematical aspect of it when people try to give an analysis or like a relativistic explanation for a phenomenon regarding a rotating interferometer, for example, which we'll get into at the end here. But this is very important because this explains how we're deviating from classical physics. So remember, classical physics, length, time, and mass are all absolute. In relativity theory, length, time, and mass are going to be functions of velocity. They're going to be functions of relative motion. Simultaneity is no longer going to be absolute. So scenarios where, you can confirm a simultaneous event occurred, but it might have appeared due to relative motion and Doppler shift that the event wasn't simultaneous, but you can confirm that it was. Well, he's saying that it's not physically valid because the sequence of events in the reference frame has to be valid. So if you are in a frame where your relative motion is going to cause you to perceive a simultaneous event in reality as not simultaneous, Einstein is going to make the argument that you have to follow that to its logical conclusion, and there's going to be a temporal divergence between the two frames, because otherwise, when you do the Lorentz transformations necessary to substantiate relativity, you're not going to be able to show reciprocity between the two frames regarding the simultaneous outcome. Because if all frames agree on the outcome, then time and space are absolute tacitly. You agree immediately. So there's no distinction between classic physics. So this is the full commitment to the divergence of the classic theory that we just learned about with the absolutes and stuff. Okay. So again, the entire paper is about examples of source and observer and clocks in relative motion to one another. The clocks aren't in relative motion to a fixed point arbitrarily defined by the dimensions of Earth or the solar system, right? It's with respect to the two phenomenon in question, source and observer. So arguments of link contraction and time dilation having physical meaningfulness. When this was proposed, this was a radical deviation from classical physics, right? They're like, people were like, are you for real saying that this is different? And there was some contention and confusion among physicists. So Einstein stepped in to clarify because one of the lads was saying, no, it's not meant to be physically meaningful. It's just kinematics. It's not real. It's not just kinematics. Einstein steps in and he's like, no, it's definitely real. And you got to admire the commitment to it, because if it's not, then none of it is physically meaningful and it doesn't change anything from classical physics. And you don't have an actual explanation to say why Michelson-Morley didn't measure what it should have measured if the Earth was moving in the way that they thought it was, in the way that they had conceptualized and derived physics. They would have been able to measure it, even irrespective of an ether, like as a mechanism, but just as a fixed point for the motion to be relative to conceptually from them. They would have should have been able to measure it. So anyway, Einstein goes through here and gives the example that based on the principle of simultaneity, if the changes aren't relative and real, then the links are absolute, and none of this, it would basically be a contradiction to my theory if I didn't say that they were real, right? So that's the main takeaway for that, because some people will say, they'll have like their own kind of custom interpretation, and they'll say like, well, it's not a real effect, it's apparent, blah blah blah. It has to be real in the frame that it's measured in, otherwise it has no physical meaning and it doesn't provide anything, and it's not logically consistent with the rest of the theory unless you interpret it that way.
What if it observes itself from the side view orthographically from the second frame? Is that still okay? Like you said, people have their own interpretation. They almost always have a custom interpretation of this part, right?
Yeah, when you go back to the source material on it, they'll be like, I don't care what Einstein said. And it's like, this is the framework that guided where you're at now. Like this,
Imagine worshiping him and then disagreeing with him on this. Huh?
Worshiping the math, but not understanding the significance of what you're calculating and the implication of it. That's the ultimate, the ultimate trick. So anyway, relativity defines simultaneity as being a function of velocity here. So specifically, he states that, and in fact, such a definition is satisfactory when we are concerned with the timing, or when defining a time exclusively for a place where the watch is located, not randomly at some fixed arbitrary point where the measurement or where the person actually is, but it is no longer satisfactory to have it connect in time a series of events occurring at different places or what comes to the same thing to evaluate these time events occurring at places remote from the watch. Okay, so they will say that if the simultaneous events disagree, you're violating causality. Well, Einstein's making the distinction here that causality, meaning like events that are that are caused in relation there that are like causally linked, meaning like your birth and death, right? You have to be born and then you live and then you die. That's the sequence of events, right? You can't die and then be born. That doesn't make any sense, right? But in relativity, an event that is not um, causally linked to you. So, like, say say you're stationary and there's a train going by you with an observer on it, and at the exact point that you two intersect with one another, lightning strikes opposite ends of the train, right? And you see that the event was simultaneous, and Einstein says that everyone says that the observer on the train would see the one that they're moving towards appear first, so they wouldn't acknowledge it as a simultaneous event, but they would all agree up until we get to relativity that in reality the event was simultaneous, but that event isn't causally linked to either observer. And what that means is that we can have two different outcomes and without violating causality. So the sequence of events in their frames has to be valid if there's no distinction between the frames being stationary and in uniform relative motion. So this is where we get into things like the twin paradox, where we have a stationary twin and a moving twin, and then they were born at the exact same time, right? So they're the exact same age, but then the one twin starts moving at relativistic speeds for a little while, and then suddenly he's 30 years younger than his twin. Well, you have to be able to Lorentz transform and show reciprocity between those two, meaning they both can't agree upon their ages at the same time. Otherwise, time and space are absolute. Or if you could only show it one way, then time and space would be absolute. So you have to have reciprocity between them, meaning the twins would have to be older and younger with respect to one another, depending on which reference frame you're doing the analysis from, which doesn't make any logical sense, sounds dumb on the face of it. I feel some of you immediately got repulsed and had a physical reaction to it. Don't worry. This is the line of logic that you have to follow if there's no absolute space to take it to its illogical conclusion, to take it to its logical conclusion, which gets real illogical, which leads to these unresolved paradoxes that come up. And they'll try and say like, oh, well, acceleration solves that. But we went through a whole Prezi on twin paradox. No one's ever rectified that. No one's ever shown a measurement where a stationary clock somehow comes out of sync proportional to a clock that was in uniform relative motion to it. So let's see. I think that covers simultaneity and spatially separated events versus causally linked events, which leads to divergent timelines. If these frames are actually equivalent, they have to lead to divergent timelines. So here's Einstein confirming in 1922 that the consequences hold mutatis mutandis, which just means vice versa for every system of reference that you're applying all the Lorentz transformation to. So in the example that he gives before he gets to this part of the quote, he's talking about clocks in uniform motion to one another. He's basically saying that, confirming like, yeah, of course this clock is younger than the other clock, and the other clock is younger than the other clock too at the same time, and vice versa. All right, so here Einstein is going over this train example that I kind of covered earlier, where we have two observers, and where there's a simultaneous event of these lightning strikes, and the observer on the train sees the one event that he's moving towards occur first. So his interpretation is that the event is not simultaneous, and this guy says it is. So when we transform, we could show that this guy says that these aren't simultaneous, and that this guy that's in motion does, right? This is the symmetry of the math that's being proposed here. But if they both agree on the event being simultaneous, then there's a contradiction and the entire framework doesn't work. So anyway, just to reiterate on the interpretation of this, showing that they're physically different, that has to lead to physically different outcomes. The point is reiterated here by Einstein in 1920 in Special and the General Theory. But he says specifically here, events which are simultaneous with the reference to the embankment are not simultaneous with respect to the train and vice versa. Relativity of simultaneity. So not absolute relativity of simultaneity, right? Relativity of simultaneity. So every reference body or coordinate system has its own particular time, right? So we got coordinate time and proper time defined by the observer in motion versus the arbitrarily defined stationary time, because it's just a, there for purposes, it's not an actual absolute time. It's just coordinate time, guys. Relax. Unless we are told that the reference body in which that the statement of time refers, there is no meaning to the statement of time of an event. Oh, no way. So that's further stating that spatially separated events can have lead to physically different outcomes without contradicting causality, because they're not linked. They're not causally linked. All right. So again, the big part of that was on distinguishing the importance between reciprocity and the frames, showing that the interpretation can't be that both frames agree on the outcome simultaneously, because that's classical physics. This is the deviation from classical physics. Okay, so if we take the example, what do I mean by like different physical outcomes? So say you have these balance beams and we have a bunch of dominoes laid around them. If you're in uniform motion relative to the stationary observer, then the ball that you see hit the beam first should cause the balance to go, or should cause it to go out of balance, and the ball should hit the dominoes, and the dominoes should fall all over the floor. Whereas the stationary observer is going to see the balls just bounce up and down and then stop and just like remain, balanced on the beam. They're not going to deviate because they both hit the balance beam at the same time simultaneously. So you have to have two different predictions, and then you would transform between the two to show that, okay, in this frame, this time, the stationary observer sees the different outcome, and this time, the moving observer sees the dominoes remain stationary, right? That's the mysticism of relativity, guys. All right, so some more notes on relativity and the proper use of the framework. Einstein notes here that the content of the restricted theory can accordingly be summarized in one sentence. All natural laws must be conditioned that they are covariant with respect to a Lorentz transformation. And covariant means, in this scenario, means that the laws of physics will remain unchanged under transformation. And that's going to be facilitated by the change in the time coordinate and the x coordinate via length contraction and time dilation to substantiate that. That relationship is called covariance. So from this, it follows that that the simultaneity of two distant events is not an invariant concept, and that the dimensions of rigid bodies and the speed of clocks depends on their state of motion. So 1940, just kind of reiterating for the boys before he taps out, what the state of the theory is and what it means. So yeah, he goes on to say here that once it was shown that simultaneity was relative and depended on the frame of reference. Oh, no way. It depends on the frame of reference. So different outcomes will, anyway, different sequence of events have different outcomes then. So every possibility of retaining action at a distance within the foundations of physics disappeared since the concept presupposed the absolute character of simultaneity. So when he says that it was shown that relativity was simultaneous, he's talking about his thought experiment that he cooked up. He didn't, no one's ever shown this or shown two different physical outcomes. It's actually preposterous and leads to cog dis in students that learn relativity theory, which we'll talk about here as we continue, because it's so counterintuitive that you have to let it go and accept that two different outcomes is mandatory. And of course, they abandoned absolute action at a distance because it would imply that there is a medium to mediate the interconnectivity there at that distance. And then, also Lorentz wrote Einstein about um, simultaneity because, even though his thought experiment was like, really cool and all, Lorentz understood that this hasn't been physically demonstrated. And as far as we know, the events are still simultaneous. So he wrote Einstein and he was like, hey, do you think that there's a universal spirit or something that permeates the entire system under consideration, which means like, the universe that mediates the interactions between all events such that it's preserving simultaneity? And Einstein never wrote him back. But basically, the example he gave was, a rest clock and a moving clock and simultaneous events. And he's like, hey, I'm having a hard time. This doesn't really make any sense. We all kind of know that simultaneity is absolute, even though there's an apparent effect that it's not. And like, I'm just not really sure where you're at with that. Let me know what your thoughts on it are. And Einstein said, hey, let me hit you back, never. And he never replied. So here we have in 2002 a paper about how it's challenging to teach students about relativity theory because they'll go through the calculations and do that properly, but they don't understand the significance of what they calculated and how to answer certain paradoxes that arise out of that because they're trying to rectify absolute simultaneity with relative simultaneity, which leads to different outcomes, which everyone's like, I'm not quite there yet, but like I'll calculate it, but I'm not really willing to argue that with my mouth or anything. But I'll calculate it. So anyway, the purpose here is showing that absolute simultaneity and relative simultaneity, do not coexist. It has to be relative simultaneity. And when they go through different examples, the students make the incorrect assessment of their calculations based off of absolute simultaneity, assuming that once they account for the timing difference between the observers, that all the frames will agree on the outcome. That's not the case. So again, when people have this conception that all the frames would have to agree and all this stuff, it's not it. That's not what is being calculated. And even in 2002, this was an issue for people trying to learn the theory or, being taught the theory. So they did like a study where they took polls from different students, at different levels of education that are studying, relativity and going through the academic pipeline. And they found that none of them really understood that that simultaneity is relative and not absolute. So here we went over the units of measurement that defined everything for the classic theory. Well, now we have time and length and mass all changing as a function of velocity here. So this is what this is supposed to represent. And these are insanely minuscule deviations, right? Like if you want to see how small these are in comparison, there's a video on BitChute by Man of Stone. You can go there and type in, is it the light propagation video, Stone? Is that the
Oh,
or is
I've
it a
been
couple thoughts about
dying to
Einstein?
mention this video for
Coup-
so long watching you talk about this.
Couple of thoughts about Einstein.
Yes, indeed. Couple thoughts about Einstein is the video. Yes,
That
thank you.
that
Thank
that's the
you.
one. Yeah, you can go through it. So this deviation from classical physics, right? This there's no simultaneity that's absolute. There's no relative or there's no motion relative to some absolute background. Nothing is absolute. This is the deviation from it. It comes down to the square of their velocity over c squared, which is an insanely small number. And to get a good grasp on that scale, check out Stone's video because it's preposterous that their entire framework of like, just trust us, this is different and explains why we can't measure our velocity. And it's like the most minuscule, minute amounts of deviation ever that they could come up with. So
To quantify it for people, it's always about the interferometer expected figure of 30 kilometers per second. But we know that we're talking about 30,000 kilometers per second at the speed of light.
Yep.
So it's literally 30 squared over 30,000 squared, so to speak, when you look at the v squared over c squared ratio, and how it is completely insignificant until you're doing 99.856% of the speed of light, which I always find absolutely hilarious. When we go back to your slide with the one with the train on it, and it says 4/5 of the speed of light.
Oh yeah.
Even doing 80% of c, the difference is just
Not even
almost
close.
unmeasurably small.
No, it's insane to get it to actually be something that you would be like, oh wow, this is crazy. There's you'd have to be moving at like 99.999.
Yeah, it's 12th decimal point to the right. Crazy.
Insane. So they've got this framework, they've got these transformations, they've got these minute deviations that they could transform between. They've disconnected simultaneous events and basically reinterpreted all the physics, but kind of kept it the same, but just changed it a little bit. And just made everything change as a function of velocity. So using that relationship with covariance and Lorentz symmetry, that was the jumping off point. So earlier we talked about how when they were doing their equations, they have to make sure that the left and right sides of the equations are all symmetrical and equal, and the dimensions are all the units are all valid and consistent. Same situation here. So now we're branching off into the substantiation of the deviation from classical physics through covariance, which is going to be a similar interpretation through the basically following the symmetry of the mathematical framework. This will substantiate whether or not you're doing a physically meaningful, description of reality to describe these contractions, dilations, and mass changes as a function of these velocities. So remember, all natural laws must be covariant under Lorentz transformation. And if you're not using a Lorentz transformation, you are not doing relativistic physics. So time and space are not absolute. Dimensions of mass change as a result of Lorentz covariance. E equals mc squared changes the conservation laws. Mass and energy become interchangeable. Let's see. And then covariance is just substantiating that physics looks the same under different inertial frame transformations.
I think this is the point in physical science where all insanity has fully engaged.
Oh,
The bottom line, bottom bullet point you got there, where mass and energy become interchangeable in formulae. That is absolute insanity. And this is why they need terms like space-time.
That was going to be my question.
yeah,
It's about space-time.
That's such a good point, such a key point, and we're actually this actually caused a huge problem for Einstein later that we're gonna touch on in regards to covariance and having issues with rest mass. Or I'm sorry, having relativistic mass being covariant with rest mass.
Another preposterous term.
Right. So here we have John Norton's analysis talking about general covariance. So as Stone was pointing out here, this is pretty preposterous on the face of it, but how can we make it worse? Can we introduce general covariance? We sure can, but we're going to get there in a second. So Einstein was more into the algebraic formulation of the transformation. So looking at this slide here, we see the algebraic transformation done. And then a guy named Minkowski came along and he was like, hey, did you know that if you take this algebraic transformation here that Einstein has, graph this out, it makes this hyperbolic, it's a hyperbolic transformation here. So we can describe the deviation from proper time and coordinate distance and proper distance as a hyperbolic, contraction here of this equation. But also, if we turn this into a three-dimensional structure, right, if we rotate this plane out, we can make a cone out of it. And we could use this, we could describe transformations as a geometric property of this space-time light cone, and everything done in here will be automatically covariant. We don't have to worry about, doing these rigorous transformations. So that was Minkowski's contribution to it, giving like a geometric way to look at the uh, what was being presented with the theory, right? So now we've got this curvature that represents space and time. And then by 1915, when that rolled around, Einstein was proposed the general theory for covariant transformations for all cases. So before we were looking at specifically uniform relative motion transformations. So the Earth around the sun, where the velocity is pretty much going to be the same and constant, even though it changes a little bit, just give it to them for funsies. So there would be like that's where that would apply, where it's going to be no change, right? Now, whether they have acceleration, they get into a situation where they're like, oh, special relativity doesn't apply to acceleration because, absolute, blah, 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 right? But remember, there's no absolute in this theory. There's no absolute in relativity, but we need a way to describe acceleration. We need a way to describe how these forces are produced in these frames that deviate from a structure where we've got the part down where there's no uniform motion, but now we need to, or no forces acting on them, but now we need to describe a scenario that would produce forces. So insert Einstein's nonlinear field equations, which is an important thing to note, which we will come back to here in a second. So the structure of these field equations starts with T mu nu here up at the top. So this is our energy stress tensor and momentum. So mass, energy, momentum, all of these things that contribute to energy, right? And because of mass energy equivalence, we can convert this all into we can conserve this into a gravitational field, right? So all we have to do, so instead of having an absolute frame for the motion to be relative to, what we need to do is devise a geometric structure that we could take differential geometric derivatives from that will allow us to describe these forces being produced by a curvature of that geometric structure. So here we're describing the conservation of energy, mass, and momentum as a gravitational field. And then that's going to be distributed as this 8 pi g over c to the fourth function. And on this side of the equation, we have the space-time curvature. So we have g mu nu and minus lambda g mu nu. The lambda is the cosmological constant. And you could set that to 0 when you're going through this. But the important part of this is the space-time curvature is going to curve in relation to the mass distribution of the universe. So remember from Mach's principle where he assumed, mass distribution of the universe will produce these inertial forces. But we're getting rid of, but we still need to get rid of like the absolute conception, right? So in order to use these field equations, you just have to assume the mass distribution of the universe, and then that will give you how much space and time are going to be curved as like an overall geometric structure. And then from that, you can take differentials from that, and they'll automatically be covariant with your overall structure because the curvature of it is going to be like defined as a like an infinitesimal sliver of it. So you can kind of think about it is the right hand side of this equation describes what it would be like to be on the inside of a basketball. And there's a specific curvature rate that defines the geometry of that ball that you're in. And if you were, but say you needed to like, zoom in really closely on the ball, you would have like a flat little section of it, right? So this is what they're doing with the math. And the curvature of space-time is going to produce these pseudo forces that they need to replace the classic inertial forces that are produced with respect to some absolute frame. So isn't that cool how instead of having an absolute frame that's the lab frame where all the laws of physics are derived, you assume that doesn't exist, has no physical meaning, even though it's the only frame that makes the correct prediction for all dynamic analysis, etc. But what you're going to trade that for is you're going to assume the mass distribution and energy of the entire universe so that you could start to have a geometric structure that you could play around with to set your sandbox. So you set your boundary conditions by knowing that there's no absolute space, but you know the mass distribution of the universe to give you the geometric properties of space-time curvature, which you then use which you then use tensors to define points in this curvature, and then you take angles between them to describe, how much curvature there was in between them, based off of the mass that's being conserved for your output there. So depending on what you're doing mathematically, how you set these tensors, how you define the mass distribution of the universe, you're going to get different calculations that are not additive, that can't be superimposed, like how you could do with Newtonian mass, how we could take 5 pounds and add 15 pounds. Well, if you derive something out of this, like a cosmological framework that describes a homogeneous distribution of mass and energy over a 14 billion year timeline, you have to make certain assumptions in the calculations for this tensor to deliver that outcome when you do the calculation to get the proper amount of homogeneously curved space-time to give you the observable universe that you're trying to say is produced by the equations that are describing it. So when you use other metric tensors, and you're setting different boundary conditions for the universe, well, if you discover something that has, new mass, a new mass value that wasn't previously accounted for in a different solution, well, you can't just add them together and impose them, because these are nonlinear. These are unique to the boundary conditions that they're derived from. So we're going to get into the significance of that very shortly. But just to kind of reiterate here, we moved from the algebraic transformations to absolute differential calculus, which is assuming like a manifold structure. So we have geometric properties, and then we take differentials from that structure that are, and because they're a part of the original structure, you're already good to go. But if you define a different structure for space-time curvature, then you're, blah blah blah. You have to do the calculations all over again. But they never do. So I hope that covers this relationship with these equations and the meaning there.
Bro, I'm confused. All right, This is a complicated question, but you ready?
Okay.
Space-time is a coordinate system, right? Is it arbitrary, or does it have physical meaning?
So arbitrary. They say that the mass distribution, so like the way that they're looking at it, right? They don't have a fixed reference point for anything, and everything's relative. But to describe the part of physics that requires that absolute frame, like the Newton's bucket situation, right? They're saying that, okay, we're not going to assume an absolute frame, but what we're going to do is assume the mass distribution of the universe. And that mass distribution is going to bend space-time. So we can use this bent structure that we now have, these coordinates that describe curvature. We can use this to describe geodesic paths,
because the curvature of space-time is the cause of gravity physically, dynamically. So that's what they're saying. Holy cow.
Well, the curvature of space-time would produce those effects, based on the gravitation, based on the, mass distribution and energy of whatever you're doing the analysis with, whatever you're tensorizing.
So I think that they would defend it. Well, no, it's not. Space-time isn't just an arbitrary coordinate system because it has real physical properties, like creating the geodesic with which gravity is formed, dude. Is that their position?
No, they specifically can't have any physical properties to it. It has to be
right. Okay.
Because if it has physical properties, then motion would be relative to it, because it would be like all encompassing. It would be some sort of medium. And Einstein even said in a paper, we said it a couple of times actually, that you can think of space-time curvature as a fluid medium, but do not dare attribute physical properties to it at all.
Yeah.
And don't assume motions relative to it, for sure.
I think if they did want to go in that direction, we'd start to see terms like mass time.
Well, I'm trying to justify
just to stick the knife in a little bit farther. Yeah.
I'm trying to justify where space-time isn't just an arbitrary nonsense coordinate system similar to the Cartesian set of cylindrical, spherical, poloidal, paradoidal that you showed at the beginning, right? Trying to separate it from that and play devil's advocate for the Globers to be like, no, precious, my space-time. No, but like, so there's no actual way to tie it to physical meaning. I think the steelman I was trying to throw out was, well, if they argue that it geodesically curves, right, and that the curvature of this geodesic space-time arc is therefore responsible for gravity, like, look, it has physical meaning, but that would contradict the first thing that Einstein said. Definitely can't have physical meaning. So then they're kind of stuck with saying that it has any sort of relevance to the physical world at all. Or am I missing something?
Pretty much nailed it. They're in what you call a pickle.
I would bring attention to what's in the gray square on 2 counts. Yeah, on the right there, the gray rectangle underneath space-time curvature. The one that's 8 pi g c4th 2077 10 to the negative 43rd exponent seconds squared over meter kilograms. All y'all, when you went to school and you got your toes into physics for the first time, what did the units of measurements look like? They looked like the reciprocal of what this unit of measurement here is. It's always meters per second, kilogram change, or whatever else per second. No. This is seconds per mass length.
What the heck is that even?
And the point is that on top of that it's 10 to the negative 43rd power. Again, we take this back to the v squared over c squared problem and what the curve that is actually produced, how much actual change is going to be happening in length or time based on that velocity of 30 kilometers per second being so remotely distant from the speed of light.
Yeah.
This is exactly the same thing going on here. This whole space-time curvature constant they're pointing out here is so direly insignificant. We will never measure it.
That's such a good point. Such a good point.
And you know what they do in addition to that? They want like even flatter sections of it. So they can have like as much fun as they want with this framework. And I think that's the appeal to it, right? Is like everyone has their own little relativity section. They all specialize in their own type of tensor calculation, and they're just having a ball, you know? You just calculate in your respective tensor, and you're basically like the dungeon master of that group. And like anyone that wants to talk about that cosmology with you, like they have to play in your tensor.
And the moment they plug in a significant figure, it all becomes completely meaningless.
Yeah.
Or has it been meaningless the whole time and they've just been tricking themselves?
Yes. So, chronicling Einstein's struggle with covariance, we have a letter here cited from Okun in The Concept of Mass in 1989 here. And this letter is from Einstein to Lincoln Barnett. Shout out to Lincoln Barnett, the geocentrist physicist. In 1948, so Einstein wrote in German. The letter that was typed is sent in English. The highlighted message excerpt says, "It is not good to introduce the concept of mass m equals m over 1 minus v squared over c squared of the moving body for which no clear definition can be given. It is much better to introduce no other mass concept other than rest mass. Instead of introducing m, it is better to mention the expression for the momentum and energy of a body in motion." So this was in relation to how he was trying to solve the conservation laws, because he actually has, in addition to the assumption of like, okay, I got this tensor that's going to describe the mass distribution of the universe. Apparently, it's been pointed out by Stephen Crothers and some others that this tensor here is actually not dimensionally valid to describe a gravitational field in the system that would curve space-time. But that's kind of above my pay grade to get into that analysis. But part of this letter here that he's writing was that struggle with the conservation laws, and he was like, can we just go back to rest mass and differentiate these two separately so this will be easier to calculate? And it's like, at this point, that's really funny because, guys, he wants to go back to absolute mass. He wants to, while still having the theory of like no absolutes, it's all determined by the mass distribution of the universe. But anyway, when we get into an analysis of the validity of the tensors and the use of this covariant relationship and what does it all mean, Basil, we have Stephen J. Crothers, who was expelled from the University of New South Wales. And you can go to his website here and read his documentation and read through the email exchanges that he had with the faculty there, up to and including a board member of the International Gravitation and Relativity Committee, which basically they're the people that are in charge of determining the interpretation of the equations and how they're, how other academic institutions are going to teach them. In relation to
set up a whole committee for that. What?
The relativity overlords.
Yes, yes. You never heard of them, dude? You've never paid homage to
the of relativists, dude.
Their robes are fantastic.
Yeah. So one of the things that Crothers pointed out in his tensor analysis, which was, like I said, over my head to get into that, but one of the things that he did point out that was really funny was in regards to black holes and how they use a coordinate label, which is, earlier we talked about the tensors are like a metric tensor is being used to define points in space-time, and then they draw lines between the points and they take angles to establish curvature and all that stuff between the points. So what they do with these, right, is he's saying that they set they have a coordinate label to, like, I'm going to put the point here. Doesn't mean anything. It has no physical dimensions or anything like that. But they put it here and they put another point there. And then they talk about like the distance relationship between these two things, that kind of thing, right? This is how they're establishing it. What they've done is they've said, okay, this coordinate label, this is actually the radius of a black hole. And if we calculate the gravitational potential at this location, it exceeds the speed of light, and that means gravity wouldn't escape from it. So they end up using this point that's defined as a function of like their math that has no physical meaning in reality. It's literally just like a point mass. It's just the thing that they're like, we need a thing here to represent something, we need a placeholder, right? It has no dimensions. But anyway, they've attributed dimensions to it, and they call that a radius, and they're like, oh dude, when the radius approaches 2m, which is their notation for their marker or for their coordinate label, they're like, that's when everything collapses and we get these black holes and stuff. So Crothers gets into a back and forth with these guys, and he's like, hey, if you want to actually derive a radius, you have to take an integral from the two coordinate points. You can't use that as a dimension. And then he derives what the dimensions would be for the actual radius of a black hole if you do it under the two coordinates, how you would normally do the integral, between the 2 points, versus doing it just with the one. And they give different distances. They're physically different. It's not a real thing. And then, so anyway, when he gets into the back and forth with these guys, some of them will be like, no, we're not doing that. It's definitely a radius. And then he'll go through the math on like something that they've published or their website or whatever. And he's like, look, here it is. This is where they're doing it. And so they are doing it. And then in other cases, they'll admit to doing it and they'll say like that they're not doing it. So there was this one guy, I want to say it was DeSitter, but it might've been something else. But anyway, this dude was like, I'm definitely not doing that. And then on his website, he's like, by the way, this is the radius of the black hole. And it's like, they all are doing this thing that like, they're not being called out on. They're doing this like dimensionally invalid, mathematical reach around to tell a story that's not meaningful.
What is the process of making a point into a circle or a radius? Don't you need 2 points at least, minimum, to have a radius? How do you convert one point into a radius?
That's what he's saying. Like when he goes through and integrals it with the 2 points, he's like, look, this is what the radius would be when he does it with the one, he's like, you get this. This is retarded.
Okay. All right.
Yeah. And then so he gets into the back and forth with these guys, and they're like, yeah, we're doing it, we're not doing it, it's okay, you know, leave us alone, don't be a party pooper. So that was the summation there. And then Crothers gives an awesome he calls it a simple non-mathematical proof, but it requires a little bit of subtext to understand. So I'm going to read through here, and then we're going to go through what he's saying. So it is very easily proven that the black hole and the Big Bang contradict one another, and so they are mutually exclusive. All alleged black hole solutions to Einstein's field equations pertain to a universe that are spatially infinite and are eternal, contain only one mass, and are not expanding, and are asymptotically flat or curved, depending on whichever they're doing there. So it's either going to be, you know, extremely curved or flat. But in the alleged Big Bang universe, those are spatially finite or spatially infinite, or they're infinite in age, contain primordial or expanding matter. They're not asymptotically anything. And thus black hole universes and Big Bang universes contradict one another. They are mutually exclusive, so they cannot coexist. It is therefore not possible for a black hole to be present in a Big Bang universe or even in another black hole universe. And likewise, it is not possible for a Big Bang universe to be present in a black hole universe or in any other Big Bang universe. Nonetheless, the astrophysical magicians superpose black holes and Big Bang universes, notwithstanding that they are not incompatible by their very definition, and that the principle of superposition does not hold in general relativity. Much of modern physics is simply manufactured in this way, and so it bears no relation to the actual universe. So when they get into,
Yo,
dude, what's up?
that's crazy. So they said that black holes, as they exist now, can't simultaneously have been created at the Big Bang in the center of all galaxies, swirling like the arc, controlling everything, and also be created at any time during the galaxy, literally by the process of, say, a star burning hydrogen, helium, carbon, neon, oxygen, silicon, all the way to iron, until that gets its own gravity and that explodes, creating another black hole, right? So those two things cannot simultaneously be true. Is that what he's saying? That's
Dude,
crazy, because they need both.
And not only that, the reason that they can't is because when they describe the structure of the universe, depending on what scale of role play they're talking about, the metric tensor that they're using to define the mass distribution of the universe. So you've heard them say things like, shout out to the Principle documentary, all the science lads that were like, well, we know the universe is homogeneous and isotropic. And it's like, well, do you know that? Or does the math you're using have to assume that because you don't want to use absolute space? And that's that's the answer. But anyway, when you make these assumptions and you set the boundary conditions for how space-time is going to be curved in relation to that, you're setting like all the mass in the universe is there. You're accounting for it, so you can't derive mass of a black hole in a different universe structure and then go, oh, that's also exists in what we're describing it from the Big Bang. From the metric that we use to describe the homogeneous distribution of mass over the 14 billion year timeline. They're incompatible.
Dude, so the stellar mass black holes are is what they need, and then supermassive black holes are supposed to be at the center. Those are the two that can't simultaneously exist, but they do, and they need them to. That's insane.
I want to party with this guy.
Dude, he's awesome. He's a legend. He challenged that one guy to a fight because what he was doing was Crothers sent him a paper, and then the guy made modifications to it and said, look, this is where you're wrong. And Crothers was like, why would you change my work and then proceed to tell me that's where I'm wrong? You're lucky I don't beat you to death or something. Like, dude, it was hilarious.
What a G.
He was like, the amount of disrespect that you've shown me is preposterous.
Way to put formulae in my mouth, buddy.
Yeah, dude, it was hilarious. So anyway, that's where we're at with covariance. So the answer to your question started out seemingly physically real and meaningful and very cool, got a little abstracted with the contraction stuff. Where are we at now with it? We're now doing mass addition to different universal structures where there is no mechanism, especially not mathematically, to add mass to the universes without recalculating the entire tensor and changing how it was derived, because it's going to lead to different predictions based off of that.
So you're saying there's a chance that it has meaning.
Just saying there's a chance. Yeah. Yeah. So what have we learned from all this? What can we do on the ground with measurements? How can we confirm absolute time and space? What's the deal? Didn't you say earlier that we can make measurements against it? Well, that's where we get into interferometry, where we have the humble Sagnac apparatus on the far right and the Wang apparatus closer on the middle left here. Now, we have this rotating interferometer at non-relativistic speeds. Oops, the circles got off-centered when I shrunk it, but the red circle here is supposed to be over this. This is where the observer is at in this apparatus. And this little circle here is supposed to be over here where the source emitter is. And we're looking at this S here is the area that light had to travel. This is the path length that it took, clockwise and counterclockwise as the device rotated. Now, when the light beam that gets split here in two different directions to itself recombines at the end of its trip here and then gets sent to the photographic recorder, it measures a first order timing difference that is proportional to the clockwise and counterclockwise rotation. So Sagnac was like, hey, boys, guess what? As per Einstein's theory of relativity, I have an inertial frame. These two are fixed to they're fixed to the rotating apparatus. They're in uniform transitory motion. There's no change between them. So they should predict that the speed of light measures no fringe here, or at the very least, it measures a gamma fringe, which would be a fraction of a fraction of a fraction of a fraction of a fringe, which nobody could actually measure at these velocities. So, insignificant, neglected term that's irrelevant. You would interpret that as no fringe. So Sagnac's like, look, no matter how fast I spin it, the fringes are proportional to it. How cool is that? I falsified relativity and showed that there is an absolute space for this motion to be relative to, because what's happening here is that they'll say, well, the mirrors are moving in position, so that's changing the path length of the apparatus. Okay. So if that were true, you would have to have an originating starting point to fix the distance to, and then as it rotates, we would have the change that would be relative to that fixed point. So that's assigning an imaginary vector to space. And remember, Einstein said we're not going to do that. So we have to come up with some way to do a Lorentz transformation to describe this. Otherwise, the whole premise of inertial observers measuring the speed of light being independent of their motion goes out the window, and there's no physical explanation for Michelson-Morley. Now, in this configuration, it's said that, well, rotation is non-inertial, it's an acceleration, special relativity doesn't apply. There's a bunch of ambiguity to it, even though Einstein specifically stated that any closed polygonal circuit in uniform rotation would constitute as an inertial frame. So anyway, we have here on the left a frame in which there only this top portion, the effective length of this chord, is going to measure a first order timing difference as it moves left to right relative to the detector. Relativity predicts that there is no relative motion here because it's a uniform translational motion, and there should be the source and the detector here are both fixed. There's no relative motion between them. This is moving at a constant speed. So remember, laws of physics and inertial frames being defined by uniform constant speed are going to be equivalent to these stationary frames that are in the lab. And there should be no relative motion between them. Yet a first order timing difference is what's measured here, even at nanometer velocities. So we have a velocity component here that's being measured that is extremely small, but it's much larger than anything that relativity could possibly ever predict as a gamma function. And due to the, go ahead.
just going to mention while we were talking about Sagnac first, even before we got to Wang, that the other video rather you mentioned of mine, talk about light propagation, actually has animation of the two beams of light going around the Sagnac one on the right. So if you guys want to catch that in action to better understand the light path.
Yeah, that's a great example of it. Seeing the light beams complete their circuit is the relevant part of this. And then, like they're saying that due to relativistic effects, that the path length would be shortened, but it predicts a much, much smaller path length change than what's predicted by the classical theory. So there's no room for relativity to explain this. And we can get into another experiment where the source and detector were fixed to the lab wall. Using 45-degree angled mirrors, the light beam is split on a disk that that uses these 45-degree angled mirrors to hit a rotating disk that will shoot them back up to the stationary disk that shoots them back to the wall where they can be recorded. And this measures the same first order timing difference for inertial observers. So here we have these are fixed to the apparatus, and like maybe you want to argue, okay, acceleration, non-inertial frame, etc. But now we have them fixed to the lab wall. They're not even on the rotating frame, and they're still measuring the path length change. So that would only be possible if this was with respect to absolute space. Which would be the ether frame. This would be that conceptual this would be that assigning imaginary vector properties that Einstein was talking about that we're not going to do. This would be that. This would be the only way to explain that. So when you get into the classical theory, it makes the correct prediction just following the old Sagnac equation. Predicts the correct fringe pattern with no modifications or changes, no reference frame transformations or anything like that. When you do the prediction for relativity theory, you make the wrong prediction by a factor of 10 for the fringe displacement, and you are essentially forced to use general relativities, a cylindrical coordinate system, and transform to the center of the device and make the motion be relative to that. And that's crazy because that's like saying this device that's rotating at like 4 times a minute or 40 times a minute, something like that, right? I can't explain it unless I invoke the mass distribution of the universe. That's crazy. It's like, how do you explain kids playing jump rope? It's like, well, we're going to have to get the tensors out and talk about the distribution of mass of the universe. Why would you ever have to do that? It doesn't make any sense. So here we have an example from Dr. Blitz, who took the challenge to do a Sagnac derivation. What he started with was a cylindrical coordinate system here using Minkowski spacetime. So he's starting off with this, fixed point in the center, takes the time coordinate from that, transforms it to a rectangular coordinate system, and then puts the observer or the detector at the center and then the other at the rim, so you could interchange them. Either one would be at the radius of this. And then basically he says that the coordinate system is rotating, and this gives you the first order plus or minus v for c with respect to it going clockwise or counterclockwise. This is no different than the classic derivation. This isn't a Lorentz transformation. This has no physical explanation for relativity. This is not derived under relativistic principles. Relativity does not predict a first order timing difference due to a coordinate system rotation. This interpretation is utilizing absolute space and then having that, having the motion being relative to that, which is going to create the c plus or minus v for them. This doesn't have any meaning in terms of deriving it without using a fictitious frame, because a fictitious frame was used. There's literally no possible way to derive the Sagnac effect using the principles of relativity theory. So when he went, yeah, go ahead.
I like how he started in cylindrical and then went to Cartesian. Like cylindrical is Cartesian, right? So you're doing a secondary transfer, like for funsies or what?
Dude. just to create the coordinate system where he would have the thing at the center just so he could spin it, right?
Yep,
And it's
'cause
like
then he had
that's
to
not,
apply the
and
metric. Yeah.
it's like, dude, this is not what relativity predicts. You're not doing a Lorentz transformation, dog, between the source emitter and the observer. It's insane. So they'll try and
Did he
say, oh, sorry, go ahead.
I was gonna say, did he submit that to you? Was that a response to something you said directly, or did he happen to put this out randomly?
No, this was a response to what I was saying in his Discord about how there's no derivation for the Sagnac effect in relativity, and it completely obliterates the theory. And he was like, no, it
Gotcha.
does. He was like, no, you can do it. And he gave some references which were refuted because Engelhardt actually shows the classic derivation, and then he shows the relativistic derivation, which basically shows that light completes the circuit independent of the motion. So there's no fringe pattern predicted, right? Very straightforward. And then so he was like, I'm going to refute that with this, and this doesn't answer it at all.
Yeah, that context helps a ton. Thank you.
Yeah, so this is just kind of showing that like the contradiction there with the measurement and how absolute space is like the only implication and way to answer this in a logically cohesive way is absolute space, through that framework of c plus or minus v, trying to maintain a constancy of c irrespective of the motion of inertial observers leads to contradictions like this. So anyway, we get into, I think that was pretty much it for that. Oh yeah, so another thing they'll try and say is like, okay, well actually, the Sagnac effect can be explained through relativity of simultaneity. Alan, that sounds crazy. What do you mean? Okay, so suppose you're on the Sagnac apparatus and you're over here at the source emitter and you're looking back at a stream of light that's coming into you, right? And the
My
stream
mom got
of
some coffee ice cream.
nice, Taylor.
Sorry.
Pick me up one too.
Sorry.
It's all good. And then so you're looking at this stream of photons that are coming at you from clockwise and counterclockwise as they're coming towards you. And you're stationary in this frame. The device is stationary, everything's stationary in this instance, right? And you see this coherent beam, you see these two coherent beams coming towards you. Now, when you start moving, right, when this beam hits this beam splitter, they're saying that the clockwise and counterclockwise splitting is a simultaneous event. And because you're in a non-inertial frame, you're at the rim of this device rotating, that you're actually going to see a series of timing separations of, if you could like, because this is in rotation, right? Let's just say you could like break it down into like any infinitesimal section of time when you're looking back at this. So as you're looking back for like a 1 second interval, let's say, you would see timing separations in that coherent beam now that are equivalent to 1 second of plus or minus variance, right? So that's their substantiation for it. So they're saying that at non-relativistic speeds, right, that relativity of simultaneity is physically manifesting in reality, and it's creating a fringe pattern because you're not going to have synchronous simultaneous events for a observer in rotation. Now that's crazy, because one of the other things that Dufour and Prunet did that contradicts this is they had a configuration such that there was a detector set on the rim of this device that's in rotation, and they had one that was fixed to the lab frame. Right. So the way that it would work out is that some of it would get split back to the detector on the rim, some would get sent back to the detector on the lab wall. They both measured the same thing. So if they both agree on the simultaneous event of the beam splitting, there can't be a fringe pattern produced by them. So any explanation of the Sagnac effect being explained through relativity of simultaneity is gone. That's invalid. Just on the face of it from that experiment alone, confirming that they both agree on the outcome. They both make the same measurement. So that's hugely significant in that. And then because otherwise, like, remember, you'd have to show reciprocity somehow. So you would have to have one frame measure the fringe, the other frame not. And then you'd have to do the experiment again and somehow show that the lab frame makes the the one the measurement of the motion, while the one that's in motion makes the measurement of stationary. Never happens, guys. It's all there's no explanation for the Sagnac effect in relativity. And then further, when you get into GPS is actually a walking experiment, a live real-time experiment of Einstein's train scenario, where GPS satellites or DGPS stations are sending signals to observers that are stationary and moving relative to one another. So they should disagree on the time that this signal was sent, because GPS establishes an absolute timeline. That's GPS time. So if you're using GPS, you're on GPS time. And if you're in relative motion to that timeline, you're going to disagree on simultaneous events. So but that's never accounted for. That's not a thing. GPS is governed by classic equations. There's no Lorentz transformations in any Navstar ICDs. There's no, in 2004, Neil Ashby was talking about how the Sagnac effect is confirmed and it's proof of relativity, and how it's proof of relativity in GPS. And then he goes on to show that he uses Galilean transformations between the ECI and ECF reference frame, which is saying that the timeline in the ECI and the timeline in the ECEF are the same. They're not using this deviation in actual time that is said to be manifest in relativistic physics at all. They're using the classical stuff. They actually go over in engineering overviews. They'll tell you that the relativistic predictions for gravitational redshift and the motion of the satellites around the Earth cancel each other out. So if that's true, and that they can just fall back on the classics, then there is no relativistic physics in here. There is no deviation. There shouldn't be able to have a synchronous timeline that observers can derive distances off of based off of the time of the speed of light. If the speed of light is independent of their distance, there's going to have to be a correction, because if their frame is valid, then the timing in which they get the signals that's triangulating their positions would be sent at different times.
Then they wouldn't need the ECI frame at all. They wouldn't need to invent a fantasy frame where the times are synchronous, specifically hiding that deviation or whatever.
Certainly gets tricky. All right, so we went over GPS and that. So the conclusion here, time and space are absolute. You can use light to make measurements against it at non-relativistic speeds, falsifying the notion of the equivalence of inertial reference frames being in uniform transitory motion, or rotation, or linear. You can use it to falsify relativity of simultaneity with the Dufour and Prunet experiment, showing that both observers agree on the measurement of the supposed difference in simultaneous events of the beam being split clockwise and counterclockwise. In GPS, the timeline is absolute. The distances derived are accurate with no Lorentz transformations, and they're actually the way that the range measurement equation works. It derives the timing distance based off of time sent and signal received. So your velocity of when you receive the signal is already incorporated in the distance that's going to be derived by the range measurement equation. So moving on from that, we have trading absolute time and space for stories about the mass distribution of the universe to satisfy the tensors of our choosing is physically meaningless, as pointed out by Crothers, not only with the pseudo tensor being not dimensionally valid to put a gravitational field in the space-time manifolds in such that it would cause the curvature to be physically meaningful, but just in terms of adding mass that is derived out of black holes and other celestial phenomenon that they're deriving under different tensors that assume different things about the universe, and that they can't be added together because they're not absolute. There's no frame for them to be relative to, or we can go, okay, we have the mass of the universe derived from this reference frame that's going to be relative to this fixed absolute point, and then we're going to add the mass distribution we're going to add these black holes in here, which assume that there's no mass of the universe and it's just this black hole. Like none of this means anything. and it's contradictory on the face of it, even without getting into the advanced math aspect of it. So the laws of mechanics are the laws of mechanics, not a singular law of mechanics, are satisfying the lab frame. So again, how they were presenting that one instance where uniform relative motion will make the correct prediction for F equals ma. They were all super pleased with that, and they this is shown not to be the case through dynamic analysis and through measurements with the speed of light. So we have, so we're going to end on the absolute lab frame and flexible ether to produce the measurements, a dynamic ether that moves with respect to the lab frame. Shout out to Cassander, who helped out with a majority of this understanding and brought a lot of this forward. All right, that was a lot. Does anyone have any questions, comments, or concerns?
Kicking some ass.
But what if I really want space-time to have physical meaning, and what if other people agree that it definitely should? Does that mean that it has physical meaning?
Ooh, if you do, you'd have to tell me where your velocity measurement is in Michelson-Morley.
Right. Well, yeah, no, just the coordinate system, just like all the other ones too. There's nothing that anyone
It's
can
just
say to convince me otherwise.
it's just a bit manifold, Shane.
It's
You know
just
when you
a
take
way
a
to describe math.
manifold and you bend it? That's all it is.
In the terms of like cosmography, you can have coordinate systems, abound, but if like unless you have a way to tie it to reality, like unless you have a datum to put it, to some sort of coordinate system that'll link it to the Earth, literally means nothing. Coordinate systems and nothing in Cartesian space can just be infinite and have just a neat way to play with numbers. So like conversely, you tie the coordinate system that you invented to handle your outrageous math to solve your ridiculous problems. Like
Yeah.
And here's your sheepskin.
how about tying space-time, meaning time as a dimension, to things like time travel? You would need space-time to be a thing for things like time travel and like every science fiction movie to exist, wouldn't you?
Yeah. Because otherwise you have a cohesive timeline that you can't go backwards from. The only thing that would like even allow that would be like you'd have to have a divergent timeline or some way to like have a manifold that describes time, and then you're gonna fold the manifold and cut out the physical difference described by it.
Okay, I could do that in a minute.
Muted you for a second, Dan. You're hot micing. Yo, Cass, see you have your mic unmuted. As a former general relativity lad, you have any input here? Anything to add?
Yeah.
Yeah, hello, Ether Rebels.
What's up?
I think you're in danger, Alan, of beginning to sound like me. It's almost like I'm hearing myself when you dig into the problems with mainstream physics, especially in this area of what's absolute motion and what's relative motion, kinematics versus dynamics. All good things like that. At the beginning, you mentioned the confusion over reference frames. And I think in one of the sentences, you said that sometimes the reference frame has an observer moving with respect to the reference frame. Well, that's impossible. The observer is the reference.
It is the reference frame. Yeah, it's a typo.
Yeah. And this is understood. It's if you were measuring something that wasn't at your location, then whatever the other location is the actual observation point.
Yeah.
So it's total confusion, and yet people can comfortably live with that inside their head. Hard to believe. Definitely, the observer is equivalent to the reference frame. Wherever the observer is taking data collection, that is the reference frame. And you can't have some other point outside of the observer called the reference frame, because then there's two reference frames. Anyway, I think that's enough about that. You mentioned linear inertial frame, which Newton believed was possible, but thought that rotation required an absolute frame. And of course, the hiker example and other linear examples contradict that. It's the laws of physics, whether they are linear or rotational, that require the Earth to be the absolute frame. Otherwise, the laws do not predict the correct results. And you went through some of the examples, and then there are, of course, are many others. Any example you take in which you have a lab frame and a non-lab frame, and they're measuring some object moving relative to them, they will disagree on the prediction. The lab frame will correctly predict the motion of the object, the non-inertial frame not. And that's basically the fundamental theorem, if you want, of alpha.
Well said.
The map, excuse me?
I said, well said.
We have the Mach principle, and you went over that nicely. That's misquoted in many cases, in many textbooks. It says that Mach's principle refers to the influence of the stars, the different stars, on the result of the Newton's bucket experiment. If you actually look at Mach's book, find that it refers to the Earth and everything else that is not the bucket. So in other words, whatever is influencing the bucket is everything that isn't the bucket, the rest of the universe, which includes the Earth. So people try to exclude the Earth when they quote Mach's principle by saying it refers to the distant stars. Well, yes, it does, but it also includes the Earth as possible inertial frame. So beware of that, where Mach's principle is quoted as only being referring to the stars. I submitted something on the off-topic channel about the, what was it, general relativity. And it covers the same point as special relativity. Special relativity predicts that we have this incredible phenomenon, which they call length contraction and space and time dilation. Well, if you consider something that's being measured with a ruler, let's say a card, playing card, and you measure that in an environment which has no gravity, so let's say far out in space, and then you bring that card down to Earth where there is gravity, and according to their theory of length contraction, you would measure a smaller distance because the distance would be contracted. What they're not telling you is that the ruler itself would also contract, so that there will be no difference if you measure something in outer space where g is 0, or on the surface of the Earth where it's 9.8, because not only does the object that you're measuring contract, but also does the measuring device. And this is true for general relativity's predictions as well as special relativity, because both of them predict that there is a change in the properties of space, the so-called space-time model. I'm glad you went over the nonlinear equations of general relativity. Basically, that predicts that if you have two solutions and you add them together, it's not the same as a linear addition of the two solutions because the equations are nonlinear. They have quadratic terms in them, and the terms refer to the curvature of space. So one of the things that you'll probably never hear general relativity discuss is the fact that adding solutions together is not possible in general relativity. Well, how did they get away with this? They say that the effects will be small and they can ignore them.
What?
All right.
No way.
Well,
dude, that's awesome. Shout out
that's
to
it.
them. That's all it took, huh? They're just small
Negligible.
and it's negligible. Wow.
I don't know, man.
That's
Sounds like a cult.
that's so cool. But like it doesn't work. It violates our structure and it's illogical based on how we even conceptualize the existence of the universe. But we'll add them together because it's negligible.
I have an off-topic question.
Yeah.
Oh, sorry.
Go
You
ahead.
can respond too, because I was gonna ask an off-topic question, so you can go ahead and respond first.
Okay. I was going to comment on what Shane's asked about space-time being arbitrary. Well, the model that they're using is that you can change the dimensions of time into space by multiplying by the speed of light, x equals c times t. Then you have four-dimensional alleged space-time in which the units are all the same. My question is, well, if you want to play that game, why not divide t by x or r, and you'll get the units of time. And then you can change all of the three space coordinates into time coordinates. And then you could have what is a four-dimensional time continuum instead of a four-dimensional space continuum. What this points out is that it's all a math game that they're playing. They're changing dimensions in order that it conform to their picture of what reality is. But all of our experiments, if they include Aether, show us that the world is a Euclidean three-dimensional space, and time is a parameter which labels each of the space events with a number which represents its time. And when we stack all of these space frames together in the order in which they occur, then we are modeling time.
Hey, I'm sorry, did y'all call me?
Go ahead, Tyler.
Okay, well, I was just gonna ask about space-time. It might be a little off topic, but is it like a real thing per se? Like, how do they invoke it, and how do they use it to explain it if it's not real? Like, how do they use it to explain anything?
Well, they need it. But that's what we're talking about, right? I was arguing that it's not real. They have nothing to justify it being real, but they invented it and said it's real. But Alan did a pretty good job of explaining where it came from, if you want to summarize.
Okay, well, I'm just wondering, like, because somebody has told me the other day, like, it's a real thing because time's real, but the space-time fabric, I don't know how they like treat it nowadays, but it's just really interesting. They were trying to say it was like a real thing.
Yeah, so trying to talk about it as like a fabric is like a teaching tool to get you to conceptualize like a bending and warping of a fabric that produces curvature. And then time, as Bennett was just talking about, right? It's like a series of events that are in sequential order. So it doesn't really have like any physicality necessarily to it, right? But it's just something that they're arbitrarily defining, and then they take that into like how he was just saying, the dimensions of the coordinate system and all of that are going to be x times ct, all that stuff. So they basically just making an abstract coordinate system that has no relation to reality, and then from that they create a manifold, right? And then from the manifold, they can take little sections of it and say, ooh, look what's going on over here in the manifold when I assign these 2 points to it, and talk about the mass distribution of energy in between them and how much curvature there's going to be. So like the curvature aspect of it and like physical meaningfulness of it is like, kind of like a teaching tool. It's not real. If it had physical properties or was anything other than an abstraction, motion would be relative to it, and that's why it's specifically, not an actual fabric.
Okay. And so, and another question, like, does the three-body problem contradict with the space-time fabric?
Good question. I think they only do two, like the analysis is only between like 2 points or whatever, I think. So I don't think they even do three bodies, and I'm not sure.
Is three-body
Because like the
Newton?
sun, it would like fall in there, right? Like it would just
Yeah.
fall.
No, Shane's right. That's more of a Newtonian analysis.
Hmm.
Yeah, it would be done
Have y'all ever-
differently because you would. So basically, what they would do differently. So in Newtonian, like how they would add up, like take the perihelion precession for example, where they took all the masses of everything, added them together, and tried to describe like a gravitational tug of war, and they couldn't do anything with that until they imposed like idealized calculations on the sun and Mercury to change space time accordingly, essentially through their boundary conditions of what they were using to solve the problem.
Have y'all ever done like a presentation on the three-body problem in particular?
Nope.
It's never been a topic by itself. It's been touched upon in several other presentations, though, I think.
I'm sorry, Shane. I'm laying down.
We've only peripherally covered it or whatever.
I try to follow along. My brain does not do physics well, but I'm learning a lot. Thank you guys. Sorry for the interjection.
Oh, you're good.
We were like, can I
Yeah.
ask a totally off-topic question? It was on space
It
time. We
was
were
it
talking
was
about
it was
space time.
super
It's fine.
it was super related and like a valuable question.
Yeah. God, JT.
Hey,
I never
Alan,
know
I
sometimes.
just wanted to thank you for all your hard work on these presentations and everything you're bringing. I also want to thank you for your humor, man. I'm listening along, doing dishes as always, and I wrote down the quote. It said, Einstein said, "Let me get back to you never," and it just started cracking up. Another another one is,
Direct quote.
I'll do the
Delegated.
math and all, but I'm not gonna say that with my mouth. And I just started dying
Dude,
laughing.
yeah, another direct
All of
quote.
this stuff is so ridiculous. It like has to work. And I'm more interested in what is going on in reality. And that's why I recommend people go to Man of Stone's channel because he breaks it down as far as you want to go. But a lot of people won't go there. They won't go and look. They're scared. So don't be that guy. Go check out Stone's videos. And that's all I had tonight.
Nice, thanks,
Many
JT.
thanks, El Presidente.
Dude, I'll do the math for you, but I won't say it with my mouth. How's that?
It's like I'll
Is that a
math
good
it out
deal?
for you, but I won't describe the physical interpretation of it. Like that's what
No, it's,
Brenner.
I'm
Remember what Brenner said? It was like if they were forced to actually tell you what they were calculating,
exactly.
they would be so embarrassed.
It was like, dude, I'll write it down and like scratch it out for you, but I will not be the one to articulate this professionally. That's really what it says.
Yeah.
I will give you the formulae, but not the significance.
Don't tell anyone I did this or whatever, you know?
Yeah, don't tell anyone I did this transformation without contacting Lorentz.
Yeah, y'all are so smart, honestly. Like, because a lot of PhD students, even who study this, like, don't go like read papers for fun. Like, even the other day, I told somebody in my lab like about this paper, and she looked at me crazy. Like, why would you go read papers for fun? But I think that's what interests me.
She's
Yeah,
like,
it
what
was
are you just
weird. Like,
independently learning and building a knowledge base? What the heck is wrong with you?
yes, it's weird. They
You mean
don't go look
nobody's
out.
paying you to do
Lot-
it?
Yeah. So true. It's so true. It's crazy. But yeah, so I think that y'all are really gifted in that you like going read papers. So yeah, thanks a lot for all your hard work.
Thanks. It's fun. It's and I'm sure since you've dabbled now in the presentation realm, the joy of sharing the Prezi is the most fun part, right?
It's instilled in you and you'll be back, right, Taylor?
Yep. Yep. So you're gonna continue to dismantle evolution in a multi-part series. You and Dan.
We're working on it, but I'm gonna
Nice.
have a debate Thursday with somebody who's anti-flat Earth about abiogenesis. So it's gonna be fun.
Who is this person that you named at Anti-Flat Earth?
Grayson Hawk.
Who?
Grayson Hawk. He's made videos apparently on like Pontchartrain, stuff like that. He's debated a lot of intelligent design proponents. So
Does
yep.
anybody know who that is?
Yeah, I spoke with him once on interferometry. He was he brought his A game, right?
All right.
So
Hey, Shane,
His name is critical base theory. Critical base theory.
yeah, that's what it is.
Oh, okay. Doesn't help me at all. I just said it like
He's
that.
hung out in Matters Now after shows a lot and has talked with Witsit before, and I think it's going to be an interesting conversation / debate. I think Taylor's going to do great.
Yeah.
She's gonna
I think
smoke
I
him.
could
I don't
take
know who
him.
that guy is.
I'm trying to. I just asked him to send me some papers, like for his side or whatever, and he just sent me his YouTube videos. And I'm like, do they have any
Yeah,
primary
just
sources in there?
Yikes.
assume that they don't know how to read papers, and you should bring like 3 or 4 papers, and you'll be fine. That'll be an evidential showing.
I have so many. I have 80 pages on a Word
Yep.
doc of stuff.
There you go. You're fine. He's gonna have his YouTube video or whatever.
I'm like, dude. Yeah.
But anyway, Alan,
Thursday?
Yeah.
did you say that was like part 1 of a 2-part presentation, or did you totally smash and kill reference frames, coordinate systems?
Yeah, so we had good timing on it, and I was like, I'll just do a full send on it, see how long it runs, and then try and speed run it on Saturday at Geos.
So I mean, that was the full thing then. All right.
Yeah, that was
Solid.
to completion.
I'm glad you covered Alan, the Stevie Crothers contribution.
Yeah, I would love to get into his first order differential intrinsic invariant situation, because that sounds like it's an awesome weapon to wield around, but it's not quite there yet.
Yeah, it's heavy math, heavy lifting. Blitz.
Yeah.
I'd sent you Sagnac analysis.
Yeah, he tried to do his
Could you
own little
send that-
derivation. Yeah.
Could you send that to me, because it sounds like he's trying to introduce a cylindrical coordinate system in order to use math to cover up
Yeah.
physics.
Yeah.
That's what I said.
No, that's that aptly described. That is the chain of events.
I was looking at it. It was like, well, there had to be some more to it, and there's not, right? That's it. You saw
Nope.
what I saw. Okay.
Nope. Literally started with cylindrical coordinate system, and then took all the variables from that, put it into a nice little rectangular coordinate system, and then said, hey, if we put the observer at the center and dude at the rim at the radius here, and we rotate the coordinate system, we're good to go. And it's like, ooh, not even close.
Yeah, I'd like to see that.
Yep, sending it to you now.
Well,
Yeah, I
And,
must say Blitz's use of technology was just blowing me away there.
Pen and paper.
nobody is over watching Professor Parks destroy Sabina. He's
No.
responding to the
No.
He's responding to the criticism of particle physics, even though he's an astronomer. He's taking
Right.
it personally, I guess.
Yeah, dude. You know why?
They would
Because
have to.
he feels bad about the accusations of having a physically meaningless job that's just dependent on mathematical interpretation through a priesthood that has no meaning other than like basically gaslighting and social shaming, so you can't critique it. So anyway, he's like, because she's part of that system too, and she's like, hey, this dude just emailed me and said and confirmed everything that everyone's been saying to him specifically over the past couple years about his profession not having any physical meaning to reality. So he's like taking it, he's going to correct that, you know, he's going to solve that or whatever.
Hey, it's important to produce meaningless papers all the time.
That's what the public wants. We want it.
Yeah. Oh. Well, at least I can see it on a replay, right?
Yeah, if you so dare.
If I want to.
Yeah. If you ever want to, like, if you're having trouble sleeping, just turn on a YouTube video listening to another man bitching. You will go to sleep so fast. All right, let's see.
Excellent presentation, Alan. Thank you.
Thank you, Lily. Where can I go to get Brushtail coffee to replenish my nourishment after such a demanding presentation? Hours of research contributed to the field of science. Where can I go to get nourishment?
Oh, yeah. Well, Brushtail coffee is excellent, especially if you add some really high quality milk to it, organic, milk to it. But I wanted to share with you guys my latest adventure with this wonderful Brushtail coffee, if you'd like to hear it. So,
Absolutely.
yeah.
Bring it on.
Well, anyways, I was sitting on my porch as usual in the morning, drinking my Brushtail coffee. And then I see this figure that kind of looked big. And that figure came closer and closer and looked to be about 9 feet tall. It was hooded with a big hooded cape and a stick with a sickle on the end of it. And I was like, holy crap, that kind of looks like the Grim Reaper. So he
No
came
way.
closer, and then it turned out to be the Grim Reaper. And he said, hey, I'm here to reap your soul. You got to go now. And I was like, what? And I had just begun drinking my wonderful mug of Brushtail coffee. And so he said, yep, you got to go. You got to go. Come with me. And I was like, what? Can I finish my Brushtail coffee at least? Like, that's the last thing I'm going to do if you're going to take me away. So he's like, okay, all right, whatever. And then he was like, oh, it smells good. And I said, would you like to have a cup? And so I quickly made him a cup of coffee, and then we were both drinking coffee. And then he looked at me and he said, hey, you got more of this? And I said, yep, I got loads. And so he was like, oh, you know what? I really like this coffee a lot. So he says, look, I'm going to give you some extra time. And so he pulled out this box. It was a round box. And then he opened up and he said, look, here are these pills, and you could just have a pill each day and you'll be fine. I'm like, what is this? It turns out those pills were space-time in pill form. So, folks, space-time is real, and you can buy it in a pill form. And you know how pills, usually when you get a box of pills, it comes with all that cottony stuff to keep the pills dry and, without smashing against each other. Well, it had this fluffy stuff and it was black, but it was not like cotton. It was like this fluffy stuff, like I've never seen any fluffy stuff like that before, and it was black. And I said, what the heck is this? He said, that's dark matter. And so there was dark matter and pills made of space time, and he gave it to me. And so, folks, I have space time now, and I can drink some more Brushtail coffee. And it looks like the Grim Reaper might be my guest to come and drink Brushtail coffee with me on many, many mornings. So I'm here to stay for a while longer with you guys. Thanks to the space-time pills and Brushtail coffee. Yay!
Dude, awesome ad, Lily. Thank you for fulfilling
Now I
your
understand.
contractually obligated duties.
Thank you. And Dr. Bennett, thank you so much for enjoying it. I enjoyed your laughter.
Is that Dr. Bennett?
Yeah.
OG Dr. Bennett?
That's his government name. We call him
The
Cass
different
around these
one?
parts.
Yeah, I know a Cass. Is that what you mean?
Talking about Cassander?
You
Just
better start
confused.
calling him Dr. Cassandra G or Dr. Bennett G. I'll send you some of the space-time pills, Doctor.
Okay.
Thank you, Alan, for another wonderful presentation.
Yep, no worries.
Putting in that work. How many hours did you spend preparing for this? I'm just curious. You don't have to say, but
I
I'm
don't
just
know.
wondering.
I don't.
He's like,
I
you
don't.
don't have to tell
I don't
me,
clock
bro.
them. Do you? Does all the time I spend thinking about it in my head in preparation to what I want it to look like in between the time it takes to make it count, or no?
Yeah,
Oh, all of it, all the time in between.
all the time.
Yep.
It's a
FaceTime?
labor of love.
He's the
Yep.
man.
Well, I judge a man by the content of his Canva project, so.
Same, brother, same. All right, cool. So we're gonna go ahead and wrap up for the night. Let's see. Tonight is Tuesday. Tomorrow is Wednesday, and then Thursday. So we're gonna be doing TikTok stuff for Wednesday, Thursday, and then Friday, of course, will be something. I'm sure. If not, there'll be nothing. It'll be a mystery surprise. So tune in to see what happens Friday. And then Sunday will be Globebusters, where Shane will do something. Or no.
Thursday is
something
Taylor's
wonderful.
debate.
Oh, yes. And Taylor's going to be debating on Thursday. So we're actually going to watch that instead of TikTok stuff, probably.
Against the globalist atheist
Yep. The worst kind of atheist.
and anti-flirt.
All right. See you guys later in the week.